I are going to die. I trust this is not breaking news. If it were, then I should have put it more gently and tactfully. Unless the substance dualists, including the religious believers in immortal souls, are on the right path, and I'm quite confident they are not, we are left with either monism or some form of property dualism. Monism implies a unity of substance. All things under this view reduce neatly to a common foundation, the physics of our universe. Property dualism, according to Patricia Churchland, says that consciousness is emergent from brain function. In Neurophilosophy, she writes, quote, "Although there are non-trivial differences among the hypotheses advanced by assorted property dualists, the crux of the shared conviction is that even if the mind is the brain, the qualities of subjective experience are nevertheless emergent with respect to the brain and its properties," unquote. Either way, we are fucked. Since my brain produces me, and your brain produces you, when the brain quits doing what it is that conjures us, in the immortal words of René Descartes, we shall altogether cease to be. What gives me solace as I contemplate my mortality is that I routinely practice not existing. I go to sleep. Admittedly, I'm apprehensive about the final transition between being and not being as it occurs in dying. But the problem of dying is that we are conscious during it, not so much that we are non-conscious at its completion. It's that bit between the kicking out of the stool and the dangling lifeless that gets my nerves up. When people worry about what it will be like after we die, as if all will be darkness or something, I think they haven't quite grasped the concept of not existing. After all, darkness is something. In this episode, I will discuss the synchrony and asynchrony of neuronal activities in the thalamocortical system to discover what can be learned about consciousness and its contents as correlates of these brain properties. In episode 5, I discussed the difference between brain activity during waking consciousness and during non-conscious states. EEG enables the differentiation between waking states, REM sleep, and non-REM sleep. During non-REM sleep, in which we expect the subject to be non-conscious, the EEG shows large, relatively synchronous slow-wave activity. By contrast, during waking and REM, we see highly asynchronous firing. This provides a nifty global correlate of consciousness. You may have observed that I carry on about the importance of integration for consciousness. Wouldn't we expect synchronous activity to reflect a higher degree of integration? The answer is yes, but I have never claimed that integration is sufficient for consciousness. In fact, when a network is synchronized, there is no capacity for differentiation, and differentiation is absolutely necessary for conscious contents. In my estimation, a system must have two components in order to be conscious. First, there must be contents. Second, there must be a point of view from which the contents are experienced. This episode is a continuation of the discussion on the intermittence of consciousness. In episode 5, I discussed the general differences between states of consciousness and states of non-consciousness in the thalamocortical system. Here, I will discuss the interplay of synchrony and asynchrony of neural activity. Synchrony refers to firing together within a brief time window. This is expected to be powerful in terms of causality because a neuron receiving many coordinated excitatory synaptic inputs is much more likely to achieve the threshold for firing an action potential of its own. Asynchrony, which is a hallmark of the EEG during conscious states, reflects a kind of fire-at-will situation, reflecting a simmering background of spontaneous firing activity across the cerebral cortex. According to my framework, the Temporally Integrated Causality Landscape, TICL, a large integrated structure of thalamocortical networks called the system has a level of integrated causality across all of its elements. Within the system, groups of neuronal elements form higher degrees of integrated causality. These are subsystems, and they provide the signal for conscious contents. These exist from the point of view of the system. So according to the framework, both integration and differentiation of neuronal signaling are required for consciousness. This is why global synchrony across the system accompanies a loss of consciousness in the case of electroconvulsive shock. In effect, synchrony is the loss of content. George Mashour has pointed out that global synchrony is a neurophysiological correlate of unconsciousness induced by anesthesia. Arguing against synchrony as a hallmark of consciousness, he writes in a paper published in the journal Anesthesiology, quote, "First, One can have hypersynchrony in the case of a seizure, but be decidedly unconscious. Second, neural synchrony, including gamma phase synchrony, can persist or even be increased during general anesthesia. Lee et al. Used electrocorticography, i.e. recordings from the cortex, of sheep during the waking state as well as during various depths of general anesthesia with volatile anesthetics. They found that local synchrony in the alpha, 8 to 13 Hz, and beta, 13 to 30 Hz bandwidths was directly related to cortical depression. Deeper anesthesia was associated with reduced cortical activation and increased synchrony. These findings are generally consistent with several recent studies of propofol-induced hypersynchrony in the alpha band, and advance the field by demonstrating similar phenomena with multiple volatile anesthetics. Do these results exclude the possibility of neural synchrony being involved in conscious processing? Not necessarily. The local synchrony observed by Lee et al. And others may inhibit or reflect an inhibition of the long-range synchrony that is thought to be important for consciousness and that appears to be differentially impaired during general anesthesia." Unquote. In epilepsy, many types of seizures are accompanied by a loss of consciousness. EEG studies in epileptic patients indicate multiple mechanisms for this effect. The signature of seizure activity is a higher low-frequency synchronous firing that often starts in one area of the cortex, such as the temporal lobe, and spreads to bilateral structures. Whether short absence seizures or the more severe and long-lasting generalized tonic-clonic seizures, there seems to be an initial localized spike discharge, followed by a more widespread slow-wave activity across much of the thalamocortical system. This slow-wave activity is reminiscent of a state of deep sleep in terms of the EEG. In the book Epilepsy and Consciousness, Hal Blumenfeld writes, quote, "Epileptic seizures are usually classified as either focal, meaning that they involve localized regions of the brain, or generalized, meaning that they involve widespread regions of the brain bilaterally. Interestingly, impaired consciousness can be seen in both focal and generalized seizures. Thus, impaired consciousness is seen in both generalized seizure types, such as absence and tonic-clonic seizures, as well as in focal impaired consciousness seizures. The three types of seizures differ dramatically in terms of their usual causes, behavioral manifestations, and brain electrical activity. However, despite the differences between absence, tonic-clonic, and focal impaired consciousness seizures, they all share a common thread of disordered consciousness and affect the same specific brain networks." Unquote. Blumenfeld goes on to propose a network inhibition hypothesis, according to which temporal lobe seizures spread to midline subcortical structures rich in GABAergic neurons that may inhibit arousal structures, causing cortical suppression. I wonder if this is a protective measure, a kind of reboot in the event of excessive neural activity as it occurs in the seizure. Whatever the mechanism, even if integration of activity across the thalamocortex is sustainable, the differentiation and thus the production of conscious contents is prevented by global synchronization. Siclari et al. Published a study in Nature Neuroscience on high-density EEG activity as it corresponds to dreaming. They awoke subjects repeatedly throughout a night of sleeping during episodes of REM and non-REM sleep. What they found was there was less low-frequency activity in posterior regions of the cortex whenever the subject reports dreaming, and increased low-frequency activity when the subject reported no experience. The findings are summarized here in the abstract. Quote, "Consciousness never fades during wake. However, if awakened from sleep, sometimes we report dreams and sometimes no experiences. Traditionally, dreaming has been identified with REM sleep, characterized by a wake-like, globally activated high-frequency EEG. However, dreaming also occurs in non-REM sleep, characterized by prominent low-frequency activity. This challenges our understanding of the neural correlates of conscious experiences in sleep. Using high-density EEG, we contrasted the presence and absence of dreaming within non-REM and REM sleep. In both non-REM and REM sleep, reports of dream experience were associated with a local decrease in low-frequency activity in posterior cortical regions. High-frequency activity within these regions correlated with specific dream contents. Monitoring this posterior hot zone predicted whether an individual reported dreaming or the absence of experiences during non-REM sleep in real time, suggesting that it may constitute a core correlate of conscious experiences in sleep, unquote. It makes sense to me that posterior areas of the thalamocortical system would be prominent in dream experiences. Frontal areas, including the motor cortex, tend to be suppressed in activity during sleep. There are normal oscillations that occur in firing activity during states of consciousness. The overall activity is high frequency and low amplitude, and it is asynchronous. But one such oscillation occurs at around 40 Hz. It's known as a gamma oscillation. Christof Koch discusses this in his book, The Quest for Consciousness. He writes, quote, "Psychologists have measured visually evoked potentials while subjects undergo visual experiences, and have concluded that activity in the gamma band indicates the formation of a visual percept, based on coalitions of neurons firing away at 40 Hz. That is, it has been hypothesized that the neuronal correlates of a visual percept are cell ensembles in the cortex that have a prominent rhythmicity," unquote. Koch says that a reduced 40 Hz component of the EEG is an indicator of anesthesia depth. He describes an important experiment on this 40 Hz component, writing, quote, "It was with a great deal of justifiable excitement, therefore, that Gray, Singer, and their colleagues described not only 40 Hz firing patterns, but also the way in which these oscillatory responses became synchronized in a stimulus-dependent manner. The scientists moved 2 bars across the receptive fields of the sites in the visual cortex of a cat where 2 electrodes were placed. This evoked appropriate spiking activity, but the exact time at which action potentials were triggered at one site was independent of the timing of action potentials at the other. The spikes were not synchronized. Synchronization increased significantly when the 2 bars were replaced by a single elongated bar whose movement could be seen by cells at both sites," unquote. This suggests that synchronization, not on a global level, but a local one, might be involved in the binding of features of a perceived object. The binding problem is infamous in the study of consciousness. Koch described it this way, quote, "Suppose I am looking at a smiling young man. His face triggers activity in the fusiform face area and in other parts of the cortex dedicated to facial recognition. The hue of his skin activates color neurons. As his head sways back and forth, neurons in a plethora of regions subserving motion generate spikes. His voice triggers a torrent of neural activity in the auditory cortex and speech-related areas, and on and on. Nevertheless, all of this disparate activity is experienced as a single integrated percept," unquote. In a review paper in 1999, Christof von der Malsburg wrote describing his temporal binding hypothesis. Quote, "How could binding be implemented in the brain? The basic idea of temporal binding is that signals of neurons that are to be grouped together are correlated in time. Neural signals can thus be evaluated in 2 ways. One of them is the classical concept of neural firing rate, in which the relevant parameter is the running average of the number of spikes arriving with any period t. The second concerns temporal correlations of signal fluctuations happening on timescales faster than t, and it is these correlations that express binding," unquote. Von der Malsburg's idea is consistent with the TICL, in that synchrony across a subset of neuronal elements would be expected to produce a subsystem which has a higher degree of temporally integrated causality than the rest of the system, which is largely firing asynchronously. I further propose that subsystems can coexist with overlapping subsystems, so that objects can be perceived in relation to other objects, or components of an object can be perceived together even as they exhibit differences of various kinds. Consider, for example, watching a car drive slowly down a city street. Clearly you perceive the car as an object, complete with its assembly of parts, its color, its arrangement of windows and doors, its overall shape and motion, but the tires at the same time are perceived to be rapidly spinning. We can see and understand this scene to have multiple levels of binding. Let's say the car is red. The windows aren't red, so it's not as if we see a large, horizontally moving, spinning redness. The real binding of features in consciousness is much more sophisticated than that. The fenders are red, the tires are spinning, the whole car is moving. This illustrates to me that there must be nested subsystems underlying the perception of the car, because the car is one thing and many things at the same time, and we are not at all confused as we watch it cruise along. What do the studies on dreaming, and epilepsy and anesthesia and binding tell us when taken together. The overall picture appears to be one of specified synchrony across smaller numbers of neurons in the context of overall asynchrony during consciousness. In the conclusion of his article in Anesthesiology, Mashour writes, quote, "When evaluating the literature, however, it is important to remember that increased neural synchrony could mean, among numerous options, the following. 1. Flexible and transient long-range phase synchrony in the gamma bandwidth, followed by active desynchronization, which is associated with consciousness. Or 2. Inflexible and persistent phase synchrony in the alpha bandwidth, which is associated with anesthetic-induced unconsciousness." Unquote. Thinking about synchrony and asynchrony was a major part of my development of the TICL framework. When the overall system is synchronized into slow waves of activity as seen in deep sleep or under general anesthesia, the system does not produce subsystems, groups of neurons firing together to produce conscious contents like visual percepts. No subsystems, nothing to experience. Anytime the system has differentiated subsystems occurring within it, having a higher level of synchrony and integrated causality on a background of low synchrony and low integrated causality, there will be conscious contents. That is, there will be consciousness. Relative synchrony against a background of relative asynchrony produces meaningful contents from the point of view of the system. We often hear talk of near-death experiences, and just as often we hear the motivated reasoning of those bringing up such experiences as an argument for continued consciousness after we die. As a neuroscientist, I just don't get the argument. Conscious contents emerge from specific activities in the cerebral cortex. Seeing a light, feeling oneself floating along a tunnel, hearing a voice, whatever the details of the near-death experience, it is assuredly arising from the thalamocortex. And as it does so, neural mechanisms of long-term memory enable the patient to recall and describe the experience. Imagine the argument that these post-mortem experiences do not entail thalamocortical function at all. Fine. I disagree, but let's follow the argument through. Thalamocortical function is necessary for the process of memory formation. The brain has undergone change, just like it always does when we form memories. Since the patient is describing their memory for the near-death experience, here and now, in a state of waking and coherent consciousness, assuming they tell the truth, they necessarily have the memory. So it seems to me you can either have thalamocortical function and a memory, or no thalamocortical function and no memory. You can't have it both ways. This means that if consciousness persists even in the absence of brain function, a real after-death experience could not be remembered and told upon the return to life.